All right, we're getting off of the pool game. We're getting off of the whatever that is, Neil Fun. We're getting off of the Hammy Home. All the games and things and stuff. Yesterday we finished 15.1. Electric field and electric force. You guys feel pretty good about that one?
Yes.
Good. Next up, you'll see on my board, we've got Coulomb's law. And then we've got some that I want to get to. We'll probably do that fairly informally. And then all the way at the bottom, the last essential standard that we have is Earth as a magnet. We covered that first semester. So we're pretty close to the end, which is good because we're getting pretty close to the end, aren't we? So that's going to work out. So we're going to go to Coulomb's law, guys. Last period, well, third period, I assigned this and I told them not to go to the questions. What do you think a couple of them did? So they clickety-clacked through. They didn't learn as much because they're just guessing and trying again until they got it right. I've got my good guardian up. Is it okay if I assign that and you guys promise not to go to the questions until we're through the lesson?
Yes.
Thank you. If you go to the questions, I'm going to call you out. All right. I'm going to make it due Monday, even though we'll probably finish like today into tomorrow. Feeling pretty good about this one. We got electric car plugged in. That's how I know it's an electric car. And then it tells me it is one. It says electric cars are becoming more popular. Well, they were on a pretty good run. And then last winter, did you guys hear the news like last winter about the electric cars?
No.
So the battery packs in most of these electric cars, they have to maintain at least a minimum temperature to be functional, yes? So what happened was through large portions of the country, I think the biggest part that I heard the most headlines from was Chicagoland, the Chicagoland area. A lot of these electric cars, if they're left outside or in an unheated garage, and it drops to 0 degrees outside, Fahrenheit, what's the battery using its energy to do?
Yeah.
Just to stay warm. Okay? Well, if you parked it at the end of your work day, you went into your house and the temperature was already cold and it dropped, maybe you only had it at 50% charge because that's what you always did. You had plenty of power to go to work for a couple more days because not everybody has a charger at their home, right? You'd go back out the next morning completely dead. So people were, like, well, this is ridiculous. Let's just get rid of these things. So there were actually a lot of trade-ins. Hertz Rent-A-Car. You guys ever heard of Hertz Rent-A-Car company?
No.
The yellow and black color brand for renting a car. Kind of big. They sold off most of their electric car fleet because, well, that's not good for business. If you rent a car to somebody, they go out to the lot to get in it and it's dead. So they kind of realigned their fleet back to hybrids and gas models. Anyway, one large advantage, though, for electric cars, it says, and I agree, is the low cost of operation. Good grief. Which may become an even bigger advantage as gas prices climb. That's true, but as gas prices climb, what also climbs?
Bills.
What does electric cars run on? Electricity. What's electricity generated from? A lot of things. We've got a whole plethora of energy sources that are turned into electricity. But number one, in most part of the country, is still what? Fossil fuels. Absolutely. So coal is still a big portion of it. Natural gas is a growing portion of it. Yeah, solar and wind and whatnot are growing too, but not at a pace nearly close. Still losing ground to the big picture. Especially now that we have these AI data centers going up that need a lot of power. You guys hear about that? Anyway, so kind of tying our lesson here into real world stuff that's happening. By the way, gas prices are still historically low if you adjust for inflation. 2008, when the gas prices spiked, they spiked to about $4 a gallon. Right now they're spiking to about $4 a gallon. Energy costs for electric cars average about 1/3 the cost of gasoline engine cars. That's true, at least as of a couple years ago when I ran the math when I had one. And then it hit a deer. But, yeah, I hit a deer with the electric car. It was a used, cheap model, and insurance covered most of it. It's fine. But they can only travel about 200 miles per charge at this point. And that's still relatively true. Usually, if you want more than that for range in an electric car, you gotta buy the more expensive extended range model. You guys, if you've looked into it at all, they've got that kind of language. These cars run using the science of electrical charges and forces. Very cool. Coulomb's law. Questions regarding the relationship between electric force, the size of the charge, and the separation between the charges were solved by Charles Coulomb in 1785. He determined that electric force between two charges is directly related to the size of the charges and inversely proportional to the distance between the charges. This is also known as Coulomb's law. Here's the formula, guys. Fe, so electric force, is equal to Coulomb's constant. That is a number that's given to us. They figured it out a long time ago, and it's still valid. It hasn't changed. And then you have Q1 and Q2. Those are the charges of two particles. And you divide that whole mess by the square of the distance. What does that look an awful lot like? What's that? Gravitational force formula, right? The gravitational force formula and the electrical force formula, Coulomb's law, they're essentially the same formula. You've got a different constant, okay? And instead of mass of two objects, you have charge of two particles. Otherwise, it's the same. The math works the same. Exactly. So we should be, because this is one of them that you guys did pretty well on, right? We ran through several examples. By the end of it, you guys were pretty comfortable with it. So this shouldn't be foreign at all. In this equation, Q1 and Q2, again, running through it, are the two charges. D is the distance between the two charges, and K is the constant of proportionality. Electrical force, Fe, which occurs as a result of interactions between two charged particles. For the purpose of calculating electrical forces, we assume all charge is a point charge, which means that the entire charge of the particle is located in a massless point, so a mathematical point. The SI unit of charge is the Coulomb, C, which is the charge of 6.25 times 10 to the 18th for electrons. Charge on a single electron is 1.6 times 10 to the negative 19 coulombs. Charge on a single electron is known as the elementary charge. So right here, oh, I had it up here. I had it. I erased it. Let me write it down again. So electron, a single electron, 1.6 times 10 to the negative 19. 1.6 times 10, was it negative 19? Yeah. And what else do I need right here? If it's an electron. Negative sign. So that's actually a typo, I believe. They left that out. So charge of a single electron is known as the elementary charge. This is the elementary charge. It's an electron. Electron charge. One electron. No, that's just the scientific notation moving the decimal point. Good question, though. Or good thought. The charge on a proton is the exact same magnitude, but it's positive.
What about neutral?
Neutrons don't have a charge. Yeah. So proton charge is exactly the same, but it's positive. Do we have to see a plus sign to know that it's positive? No, it just might be absent. Good. When the charges are measured in coulombs, the distance in meters, and the force in newtons, the constant K is 9 times 10 to the 9th. So our constant is 9 times 10 to the 9th, and that's Newton, let me make sure I get this right, Newton meters squared divided by Coulomb squared. But when we were putting it in the calculator, I'm not going to focus on the units as much as maybe I should. You guys are being awesome, by the way. A lot of you taking notes, right? Oh, I look guilty. I was like, oh, sure I am. No, not you. You're hanging out on the computer, right? Yeah. The electrical force, like all forces, is a vector quantity. If the two charges are considered, or excuse me, being considered, are both positive or both negative. So if they're like charges, what do?
Separate.
They repel. They separate. They repel. Like charges repel. So it's repulsive. If the two charges are opposite, they attract. So if you have a negative sign, that's them attracting. Right here it says a negative sign, force will attract. If you have positive force, so your newtons are positive, you have it's the same type of charge and they're repelling. So positive force, because when you get this electrical force, it's going to be in newtons. If you have a positive value there, that means they're repelling each other. You have the same type of charge. If they're negative, that means they're attracting. Does that make sense? Kind of, sort of, maybe? Harden, could you stop playing blocks or is unblocked?
I love that game.
Well, that's fine that you love it. You can play it on your own time. Okay? Because I know you're guilty sometimes of clickety-clacking through the quizzes, and I don't want you to have to do that. All right, so that's the reading, guys. We're done with the reading. Oh, but there's a little more. No, that's just saying there's going to be a simulation. I'm going to do this summary, and then we're going to run an example. Sound good? Okay. Summary. Coulomb determined that electrical force between two charges is directly related to the size of the charges and inversely proportional to the distance between the charges. Very similar to the gravitational force formula. The SI unit of charge is the Coulomb. The charge on a single electron is negative 1.6 times 10 to the negative 19 coulombs and is known as the elementary charge. The electrical force is a vector quantity that is positive if the particles are repelling and negative if they're attracting. Questions on that? Make sure it's in your notes if it's not in your forehead, brain, yeah. All right, let's do, they've got an example worked up here. Let's just go straight to one and work it. We're going to do number 4. And please keep the giggling to a minimum. Golly, third period. Could not get over this question. A red foam ball and a blue foam ball are 4 meters apart. So we have the distance. Yes? Okay. So we're going to put that distance at 4 meters, and that's supposed to be squared, right? First pieces of information. The blue ball has a charge of 0.000337. 0.000337 coulombs. I'm going to put that in parentheses. That's one of our charges. It's attracting. Notice there's no negative sign on that first one. It says it is attracting the red ball, which means the red ball must have what type of charge? Must be negative. Very good. So we're looking for another charge that's going to be, so Q2 is going to have a negative charge on it. So just keep that in mind. And then we're given the force. So out front we have the force, 626 newtons is given. And then what's the last thing I need to put here? The K, the constant. So we're going to squeeze this in here. 9 times 10 to the 9th Newton meter squared divided by Coulomb squared. I'm just not going to write that all there. So how do I solve? Anybody tell me the first thing I need to do to solve this one? We're looking specifically for this, but I can just solve the whole what? First. The whole top. The whole numerator. It basically what we're doing is we're treating this whole top as solve for x. Does that make sense? And then once we have that, then we can set the numerator equal to what the numerator is. So I have my quotient, I have my denominator. How do I find the numerator? It helps sometimes to think out loud. X what divided by 4 squared equals 626. By the way, what's 4 squared? 16. So if here is dividing to get this, how do we like undo that? What will we do? Multiply. Try it. So 626 times 16 would give us what? 10,016. And we're going to set that now equal. We can just like stop looking at these, right? They're still there, but we don't need to look at them. Now we're going to set this equal to what we started with. So we have our 9 times 10 to the 9th. We have our charge. And we have our Q2, our second charged particle. So we're looking for that. And I'm going to stick this negative sign here to remember that we are looking for a negative number there. Has to be negative. Okay. Now what? Multiply? Could we multiply first? And if so, what? So there's a couple ways you could do it, right? I could multiply these first and then take that product and divide this number by it. Or I could divide 10,016 by this one and then that answer by this one, right? I could do it either way. Which do you prefer?
Second way.
The second one? All right. Keep it kind of sort of simpler, maybe. So we're going to divide 10,016 by 9 times 10 to the 9th. What do I get? Anybody with a calculator? Which is like all of you because you have computers. So even if you don't have a handheld. In fact, I'll give a little pause so everybody can get it. And then when somebody answers, you can be like, yes, that's what I got too. You got it? You gonna put anything in the calculator? Just waiting for your neighbor to do it. You're taking 10,016, which is what the numerator is equal to. And then we're going to divide out the two known variables to find the one we're looking for. So what's 10,016 divided by 9 times 10 to the 9th? A lot of numbers. Give them to me. Wow. Is there anything after that? No.
Well, times
I need that. Yeah, times 10 to the 11th. Okay. All right. Now I'm going to divide that by my other variable I need to get away. I need to isolate, right? So I'm going to go divide that by 0.000337 coulombs. What do we get? Anybody? I've got some folks that have shut down completely. They've closed their computers. They are done working for today. I'm literally just asking you to put numbers in your calculator. It's a lot of numbers. What did you get? And now we're going to have our Q2 equal to. What are we equal to? Whoa, too fast. 981.
8661 times 10 to the 14.
Okay. So our charge, and I can just move this negative sign over here, can't I? That's our charge on the red balloon. Done. Is that super easy or super hard? Somewhere in the middle, maybe? Super hard. All right, let's, did I assign it?
Yeah.
Did I assign it? Yes or no? Okay. So go ahead. You guys are free to, by the way, you're free to go back and do the simulation. You're free to go back and look through the examples. Oh, I have a print-off sheet for you too that has an example using the formula. So you have something like tangible. You can incorporate this in your notes. And it actually compares the Coulomb's law to gravitational force. Kind of neat.
Wait, so we can or we can't?
Yes, you may. When you're ready. If you need to do the simulation, I would highly recommend it. And you can keep this for your notes. Guys, you will see one of these electrical force, Coulomb's law formulas on a quiz. I will let you use this sheet. Take your time. If you have questions, are you allowed to ask me?
Yeah.
Yeah. What could you do maybe before asking me? Ask Flexi. Ask your assistant. And if the hint doesn't help, then you can certainly ask me. Oh, did I miss one? Yeah, the process is the same. Try not to clickety-clack, guys. Don't guess. Ask for a hint. Go back in the reading if need be. If you still don't know, ask me. I've got a couple of you doing the interactive. That's great. Got a question?
Must be like a distance of 4. It's to the left, to the right.
It's asking for net force. All right, hey, so good. First question. If you come across this one, you'll already have the answer. I don't mind. Guys, I told you I don't mind working them. So on the board here, I'm going to draw this out. It says you have an origin point and there's a proton there, yes?
Yes.
It says 2 meters to the left, there's an electron. 2 meters to the right, there's an electron. What's going on between the electron and the proton? They're attracting. What about this proton and electron? They're attracting. So it's being pulled, they're being pulled towards each other, yes? Okay. Oops, did I do that wrong? Being pulled toward each other. How far to the right?
2.
2 meters. How far to the left?
2.
So would we say that the pull is equal on both sides?
Yeah.
So what could we, like what language would we use to describe? If they're at equilibrium, okay, they're pulling equally from both sides, which means the net force applied on the proton is what?
Equal.
Equal from both sides. So the net would be 0. They cancel out. Does that make sense?
0.
Does that make sense?
Yeah. No, makes sense. Have you noticed how good I am?
I've noticed that the whole class seems to be working a little better than maybe lately. Just you. Yeah, it's just you. Yeah, maybe. Working?
Brody Phelps, please report to the front office. Brody Phelps, please report to the front office at this time. Thank you. Brody Phelps.
He reminds me of Brock Purdy. He looks a lot like Brock Purdy. Like they could be brothers for sure. What's up, Long? Is it on your screen right now? Can I borrow your screen? If I can find it. Oh my heavens, where are you? There you are. All right. Shh. If 2-point charges, both of charge 3 Newton coulombs, or no, nano coulombs.
What is that?
It's a small version of a coulomb. So you know how like you have like millimeters, for example. Nano is a smaller unit. All right. We have 3 nanocoulombs are placed 0.01 meters apart. What is the force between them? Now, if it's in nanocoulombs, will we have to convert that back to coulombs?
No. Yes?
Probably need to convert that back to coulombs. So you probably want to Google that because I don't remember what lesson it's in. It might be in your notes from earlier this year, but I don't remember if we went to nano. So see how far you need to move that decimal place to make it coulombs, and then we're just solving for force, and it reminds us that the constant is the 9 times 10 to the 9th. So plug it in the formula, this formula right here. So you have 2-point charges. They have the same charge. So convert it to coulombs and put them both right there. And then your distance is 0.01 meters, and make sure you square it. Yeah. You're solving for force. Yes. If you need to go, you need to go. Goodlet. Were you paying attention when I did this? So you have your source, your origin with a proton, 2 meters to the left and 2 meters to the right. You have an electron. So they're pulling equally in opposite directions. So those pulling forces cancel out. Running into anything?
No.
That's good. Snap out of it. Smith, are you done? Okay. Did you get a chance to look at the interactive? Since you're done, did you already look at the interactive? Oh. You can get away with it, I think. Harmony, good job. I was watching you and your gears turning because they looked almost the same, but one was multiplying and one was dividing. Good. Question? Let me find your screen again. There you are. How is Coulomb's force between two charges affected when each charge is tripled and the distance between them is also tripled? Shh. Extra conversations need to stop. Are you done? Okay, so keep working. We don't need to be gossiping. If we triple each charge and the distance between them is also tripled, would everything stay the same? I'm trying to think if this is one of those questions that you can just think through rather than doing the math. We could make up numbers and then do the math. Does it stay the same? Is it like, does it cancel out? If you triple everything and then, but you triple the distance too, it cancels out, doesn't it? Hey, remember gravitational force? Remember what happened when we doubled the distance? Remember the distance, but then the distance is, it's squared. It's inversely proportional to the square of the distance, not just the distance.
Yes. Did you see how good it?
It's pretty easy, right?
Yeah.
Yeah. I also like the equations that it's just one easy thing. This is actually not that difficult because it's a single step. But if we had other things, remember some of the weight stuff we did require us to do multiple steps. Good. It's kind of a dead giveaway that you guys are on your phones when it's just you're just staring down at your lap. A couple of you are finishing, that's fine. If you've got other work, I would much prefer you to do that than hop on a game or study. Or if you had any questions, you could ask them. Is it possible you could get the right answer but still have a question about it? Sure. Right in your way. She sleeping? You done? No? Head up. Do work. Done? Awesome. You got other things to work on? I don't really have enough time to give you just an add-on. So again, if you've got a little prefix before a Coulomb, they've modified that unit, right? So look up, ask for a hint perhaps. It would probably give you how to convert from that. What's that symbol called again? I forget. We used it earlier this year. No, this guy right here. Oh, I'm sorry. A mu, isn't this called a mu? The U with the dangly bit out front. So that's a prefix to alter the meaning of that. So I'd have to look it up. So, but I bet you if you ask for a hint, it might give it to you. Oh, it's not. Golly. Google it. Google that. It's called the mu, that Greek letter, the U with the dangly bit. What did we do earlier this year? Let's. Metric prefixes, right? And we should find a chart with that symbol. Here we go. Right there, micro. It means micro. So you'd have to move the decimal place 6 places, okay, to convert it to coulombs. Oh my! Get off my screen. Guys, we still have some folks working. If you're done, that's great. Find something quiet to read. You have something to read? You got enough time? You could read a little bit. So read it. Instead of saying you like reading it, read it. So do it. Shh. You're not even done with the lesson yet. Are you done? Work. About half of you are still working on the lesson. That's good. Don't try to rush to finish before the end of class. If you have questions you want to ask me tomorrow, that's fine. Hey, guys, keep your hands on your own computer and off of your neighbor. Husband, I'm looking at your screen more than you are. You need to convert that back to coulombs. You're going to move your decimal place. The exponent there is -9 times 10 to the -9. Do you understand? You're going to move the decimal to the right 9 places to convert it to coulombs. But is what?
SI.
SI unit, Standard International Unit. We learned that like first 2 lessons of the year. What's up? You got it? Did you get it by clicking or did you get it by doing the math? Good. Oh, in your head. Suspect. Oh, you did use a calculator. Now you're changing your story.
Yes. It says it's wrong.
What'd you do?
It says, what is the SI unit of electrical charge? I said Standard International.
No.
We just
What
saw-
you said? What's the SI unit? SI stands for Standard International.
Oh, are you
What is the unit?
the elementary charge? Is that
No.
it? I'm not getting it.
It's in the reading. We read it. Go back to the reading. And there's a hint I'll give you. The hint, the name of the lesson today was Coulomb's law.
Is it the F E equals K Q1 Q2?
That's the formula.
Oh, is it the 9 times 10 to the 9th?
You're asking for the unit.
Oh, wait.
There it is. Hey, when do we get ready to go? Not 31. You're a couple minutes early.
Autocorrect it to Columbus.
Well, don't let it autocorrect. If you need to know how to spell it, look back in the reading.
No, I know how to spell it.
Okay.
It's autocorrect. Coulomb. Then it said it's reference Coulomb.
Yep.